colloquium. Today I'm coming to you live from my apartment. I'll just quickly explain the rules of the colloquium before I pass off to the host, who will introduce the speaker. So the colloquium will be a 45-minute talk, followed by 15 minutes of questions. And at around 4:30, there will be an après colloque, where professors will be asked to log off. The recording that is happening now and the live stream will stop. And undergrads, grads, postdocs, and others who have joined who are non-faculty members will have the chance to talk to the speaker in person. I should remind everyone that this session is being recorded and that it is being live streamed currently on YouTube. And so if you don't wish to be recorded or live streamed, please log off and go to YouTube. We're trying a different format from last week's colloquium, where you have the opportunity to unmute yourself. So please do not abuse the power. If you are not speaking at any time, please mute your microphone. You will have the power to unmute your microphone yourself. When you ask a question, if you feel it's okay, please feel free to turn on your video, or otherwise, if you want to turn on your video, the speaker can see your face. It might be easier for the speaker. Okay, with that, I will pass the baton to Professor Simon Caron-Houel to introduce the host, or introduce the speaker.
Yeah, thank you. It's a pleasure to introduce Nima Arkani-Hamed. So Nima is a high energy theorist in high energy in every sense of the word. He got famous early on in his career for the idea of the possibility, the idea of large extra dimension, which is the possibility that there could be a fifth space-time dimension that could be even as big as a millimeter, and yet would have escaped all detection by condensed matter and collider experiments. He had a lot of creative ideas about the standard model Higgs particles and how it could possibly have differed from the standard model Higgs that now appears to be. Is very broad. So when I met him about 10 years ago, he was also starting to work on topics that are much more formal, including quantum gravity, and he was he's been working a lot on models of concrete models of our space and time could emerge from more basic notion. I believe we'll hear much more about that today. Nima is the recipient of many prizes. I will name just one of these. He won the inaugural Breakthrough Prize in 2012. If you look up that prize, you may guess that this event may have added a couple of zeros in his bank account. One thing which is very impressive is that when you look at Nima, it doesn't show at all. So, well, you can't see him yet, but yeah. Perhaps most importantly, when you see him speak with people that are on physics, in physics or on the streets, he remains very generous person, so he hasn't changed at all. So this is a message for all the students and postdocs in the room. If you can stay for the après colloque, I really invite you to do so. I'm sure, even if you're from a different field, I'm sure you will have a lot of fun. So please, Nima, take over.
Thank you very much, Simon, for that extremely nice introduction. Let me share my screen here. I'm really delighted to be able to be joining you, even if only virtually. Can you guys see my screen? Is my screen visible to you guys?
Yes, yes, it's
okay.
visible.
In fact, I think the last time I gave a colloquium at McGill was around a little over 10 years ago, I think, which was exactly when I just started thinking about these new directions. So so it's sort of nice to come back 10 years later and give sort of a status report on what's going on. So yeah, I'll be giving a quite broad overview. It's really impossible to talk about this subject, you know, in detail in 45 minutes or an hour. But I want to give you, what I want you to get out of the talk is first a very clear picture of what the motivations are, what the sort of big picture goals of this general approach to thinking about these questions are, and at least some impression of what some of the more detailed ideas are actually like, because it's really the sort of concrete instantiations of this sort of general program that of course make it interesting and give it some teeth. So this is work, as I said, that I've done over the past a decade or so with a wonderful group of collaborators, of physicists, both physicists and mathematicians. I've listed a group of them here. I won't be giving references as we go, but anyway, the work has many antecedents and is continuing with a number of interesting groups of young and old collaborators. So let me begin. We're going to be doing very, sorry, 1 second. I'm having difficulty. Hold on a sec. Sorry. Let me see. This wasn't giving me trouble before, as always. Let me see what happens when I try this again. Okay, good. We're going to very quickly be talking about more concrete things. Oops. Guys, it's telling me that Zoom quit unexpectedly, but can you hear me okay?
We can hear you very well. I don't know if you can hear us. Can you hear us?
Oh, okay, we great. Then I guess Zoom didn't quit. Okay. All right. Sorry about that, but I'll just ignore that. All right. I'll just reshare my screen. Sorry for the difficulties, technical difficulties here. Yeah. So let's.
We seem to have lost Nima, but hopefully he'll be able to rejoin.
No, he's there. He's just muted. Nima, I think you're muted.
Yeah, I think my Zoom seems to be deciding to randomly mute me and tell me that it's crashing. All right, let's see if this is okay. All right, you can hear me okay, right?
Yeah.
Okay. Yes. All right. So just a bit of a broad context. Of course, the 20th century started with these two revolutions in fundamental physics of quantum mechanics and space-time, and the union of these two ideas is the general theoretical framework of quantum field theory that lets us talk about universes that are compatible with both the principles of quantum mechanics and of special relativity. And these principles are sorry again, guys.
Yeah, you might need to share your screen again because we can see and hear you, but not your slides.
Okay. Yeah. We were not having this trouble at all when we checked things before, naturally. Okay, let's try this one more time. Actually, I wonder if it'll be better if I just do, hold on. Let me just try this instead. Maybe that'll make it a little better. Okay.
Yeah, so we can see that.
Okie dokie. Let me just go to full screen then. Okay, now what's important is that I be able to advance. Okay, I can advance. All right. And those principles of quantum mechanics and space-time and quantum field theory are spectacularly successful, which is what makes it particularly fascinating that there are storm clouds on the horizon that we've known about for a number of decades that actually aren't about the technicalities, but go right to the heart of these two foundational ideas. We have reasons to expect that there's something wrong with these two basic ideas on which all of the spectacular edifice of modern physics is based. It's very likely the notion of space-time is approximate, it's doomed, it has to be replaced with more primitive ideas. And it's even conceivable that we have to talk about limitations of quantum mechanics ultimately when it comes to deep questions about cosmology. I won't talk about that too much. I'll focus more on the issues about the doom of space-time. There are many thought experiments that tell you that, that the notion of space-time is approximate. Here is a famous one. Let's say you're trying to look at some small region of space and time and resolve what's going on. You want to use a magnifying glass to see what's going on in the vacuum on some distance scales of order delta t. The uncertainty principle tells you need to use an energy of order 1/delta t to probe this small region. So you need higher and higher energies to probe shorter and shorter distances. And eventually something bad happens because of gravity. Eventually you put so much energy into such a small region of space that the region you're trying to look at and resolve actually collapses into a black hole. And if you get frustrated and use even more powerful magnifying glass, even higher energies, what happens? You make an even larger black hole. So that means there's no operational meaning to talking about distances and times that are smaller than a critical amount that's given by this famous Planck length around 10 to the minus 33 centimeters, 10 to the minus 43 seconds. So this is one, as I said, very simple and famous thought experiment that says that because of gravity and quantum mechanics, we can't even give operational meaning to the notion of space-time to perfect accuracy. And every time it's happened to us before in physics that there's some notion that we can't even in principle give operational meaning to, it is meant that that notion is approximate and has to be replaced by something else. There's actually an even, in some sense, related but even deeper issue with limitations that gravity and quantum mechanics puts on our notions of space-time, which is that if you try to make any kind of observation in finite regions of space and time, quantum mechanics asks you to talk about sort of perfectly precise quantum mechanical observables. You have to imagine that the quantum system that you're looking at is interacting with an enormous apparatus. In fact, parametrically, an infinitely large apparatus. Otherwise, there is uncertainty associated with the quantum fluctuations of the apparatus itself. So that's what quantum mechanics asks you to do. You've got to drag around this infinite classical apparatus with you everywhere you go, but gravity doesn't like that. Everything gravitates. You can't decouple the apparatus from the system. And if you try to make an experiment in a fixed size room, and you try to make that apparatus bigger and bigger and bigger to make your experiment more and more perfectly accurate, before you can make the apparatus infinitely big, it gets heavier and heavier and it collapses the whole room into a black hole. And so that puts a limitation on any kind of quantity you can talk about in the interior of space-time. That's why it's a deep fact about quantum mechanics and gravity that the only kind of observables we're allowed to talk about are anchored to the boundaries of space-time at infinity. Because there you can at least take the apparatuses, move them far apart, have them become as big as possible. They can fire particles into the interior of the space-time, bang into each other and go back out. But those kind of observables in flat space, there would be scattering amplitudes, scattering processes where particles come in, bang into each other and go back out. These are the kinds of things that we're allowed to talk about, but not sort of local observations in the interior of space-time. Okay, so that's one sort of conceptual importance of scattering amplitudes. Of course, they have a very practical importance in the experimental exploration of high energy physics. So, you know, we think about particle scattering as a more basic process in nature all the time, and it's very, very important for the experimental exploration of high energy physics. So we're doing scattering experiments at the Large Hadron Collider, for example, all the time in order to see what's going on with the laws of nature at very, very short distances. So they have both practical importance and also they have this conceptual importance as being the kind of observables we're allowed to talk about when we have quantum mechanics and gravity that are anchored to the boundaries of space-time and infinity. Now, this basic fact that when you have quantum mechanics and gravity, the only things you're allowed to talk about precisely quantum mechanically live at infinity, while at some sort of qualitative level was appreciated by a few people in the 60s, it exploded into the theoretical consciousness of theoretical physicists and string theorists, especially in the late 90s, in a cousin setting where the universe that we talk about doesn't look quite like our own. It's like the inside of this box, the inside of this cylinder, and it has the interesting property that the space inside is curved. So while the distance from a point in the interior out to the walls is infinite, it takes light a finite amount of time to go from the interior, bang into the wall, and bounce back. So this is wonderful because it's an example of a sort of a theory that is quantum mechanics and gravity that lives in a box. And physicists are very, very good at thinking about things that live in boxes. So once again here, this general philosophy, it's often called the holographic philosophy, that the things you're allowed to talk about only live on the walls of infinity, tells you that the only experiments you can talk about precisely are sort of pinging things on the walls, having excitations go into the interior of the space, bang into each other and come back out. But you can ask, since the experiment starts and ends at infinity, is there some way of describing what happened without ever talking about the inside? And remarkably, the answer is yes. that a completely ordinary theory of particles interacting with each other, very much like the quarks and gluons of the strong interaction, except when you crank up the coupling to the enormous, a completely ordinary theory of that sort, that just a particle theory of that sort that just lives on the walls of the box. If you ask that theory answers to this question of what happens when you ping the box and how the system responds to being pinged, it's exactly as if, like a hologram, there is an interior emerging. There's the interior space emerging, and the simple way of thinking about the physics, at least in a limit where the interaction between the particles is incredibly strong, is to actually think that there is this extra space arising, and there's gravity and strings and all the rest of the stuff that we expect we need when we have quantum mechanics and gravity arises in this way. So this is absolutely fascinating. It gives us a sort of first step in the general direction that we want to see sort of space-time emerging from more primitive ingredients. But there is one important thing missing. It's space that's emerging in this example. So you can think of it as a setup where quantum mechanics is king. There's a completely ordinary quantum theory of these particles interacting on the walls of this anti-de Sitter space box. And the strong interactions of this quantum mechanical system sort of as an illusion or a hologram produce the emergent space. But the time that flows on the walls of the box is exactly the same as the time that flows in the interior. So we're still not understanding the emergence of time. And that's not academic. Our universe is not a static, infinite inside of a box. Our universe is cosmological. We had some beginning in a Big Bang. We even have very puzzling questions that are forced on us by the fact that the universe is accelerating today. And we could have an entire colloquium just on this on the nature of these questions, but suffice it to say that both the question of what happens at the Big Bang, as well as actually trying to figure out how to make sense of the essentially sort of finite universe that's forced on us by the fact that regions that are sufficiently far away are accelerating away from us so that we can't actually get information from them. Both of these things expose enormous conceptual challenges. And it's clear that we have to understand not just the emergence of space, but the emergence of space and time. And the second time emerges, sort of everything is up for grabs. This is a more speculative statement, but I certainly believe that to really make sense of these things, we need some extension of quantum mechanics. Not that quantum mechanics is wrong or needs to be modified, but it's impotent to tell us how to answer these particular kinds of questions about accelerating universes. And we might need to figure out how to extend it in some way to help us deal with these conceptual issues. So, what I suspect is needed, and what we've seen an example of, is how quantum mechanics can give rise to space. But I think that even more futuristically, what we ultimately want to see is some maybe more abstract set of ideas. We don't know what they are, but they're going to give us emergent space-time and quantum mechanics at the same moment. So we'll see that there are some more abstract set of ideas that not that quantum mechanics is king and space emerges, but that there's some other set of ideas, and out of them emerge both quantum mechanics and space-time, sort of joined at the hip inexorably together. So that's a speculation that has a number of qualitative reasons to believe it. And towards the end of this talk, we're going to see very concrete, baby toy, but very concrete examples of how this could happen. And I want to stress again that what's really important here is the mystery of time. For instance, if we go back to talking about those scattering processes, the main thing we don't understand is the following. You throw the particles in from infinity, they go back out to infinity. You didn't follow the particles in, you didn't see what happened. First this happened, then this banged into that, and so on. You just see the outcome of the final experiment, in to out. And it's just given that information of what you can measure at infinity, how can you tell whether the physics that took place in the interior was actually compatible with causality? So this is sort of a deep question. It was really first posed in the 1960s. And we still don't know the complete answer to this question. Sort of shockingly, in the 2020s, we still don't know the answer to the super basic question about the way the real world works. And in the 1960s, there was something called the S-matrix program where people wanted to sort of directly determine these amplitudes, but they hoped that they would learn what these rules about what causality were. They hoped they would be able to derive them sort of responsibly, put on their Girl Guide caps and, learn responsibly what these rules are. And they failed at doing that. What we've been doing in this business over the past decade, as again, antecedents going back longer, is in a sense the reverse. So instead of trying to responsibly derive what the principles that enforce causality are, et cetera, on the amplitudes, we have a new strategy. We want to look for some new principles, new laws, new structures that actually give us the answer directly. And then we can read back out how what we normally think of as causality and unitarity, the usual rules of space-time physics and quantum mechanics, how they emerge from these principles. And as I said, how they sort of emerge together. So the kind of the general question that we're asking is, again, imagine that you just threw the particles in from infinity, they went back out to infinity. You don't know what happened in the middle there. If you're an experimentalist, you just do this experiment. And if the theorist who comes along and tells you, oh no, what happened is that the particles went in and they banged into each other in this way, you draw these pictures, Feynman's diagrams for what happened in the middle. And the purpose of these pictures is to make it clear that there are local interactions in space and time. And then you have to add up all the pictures in order to be consistent with Feynman's picture of quantum mechanics, sort of summing over all possible histories of how this process happened. So that's our usual picture. It's a theorist who comes in from the outside and tells you this is what's going on the inside. And our purpose is to find something else that does that. We don't want to take the rules of quantum space-time and quantum mechanics for granted. We don't want to do it because we suspect ultimately, because of gravity and cosmology and these deep issues, that we're going to have to replace them with something else. And that's such a radical step. It's kind of like the step of going from classical to quantum mechanics, where we have to give up determinism. This is such a radical step that it seems unlikely it'll leave, the rest of physics unscathed. It must be that there's some way, if there really is no such thing fundamentally as space-time in the deeper description of physics, there should be some way of talking about processes that we think crucially rely on space-time in a space-timeless way. And similarly with quantum mechanics, things that seem to crucially rely on the existence of a Hilbert space, we should somehow be able to describe in a way that does not rely on that, if those notions are eventually have to be replaced by something else. So this is a strategy. There are a number of other strategies. This is a rather indirect strategy to try to attack these questions. But that's what we're going to try to do. We're trying to look for evidence in ordinary established physics, but learn to talk about ordinary established physics in a way that does not put in what looks like space-time and quantum mechanics by hand. And if we can do that, we can then try to see how this something else gives rise to the properties of the amplitudes that we ordinarily ascribe to space-time and quantum mechanics. All right, so that's all very sort of highfalutin. I now want to give a much more down-to-earth and concrete indication that something like this, that it's worthwhile looking for something like this. So let's go back and talk about particle scattering at the Large Hadron Collider. And something that every experimentalist knows, if there are any particle experimentalists in the audience, they'll kill me for this incredibly simplified cartoon of what's going on. But when we collide protons at the LHC, we're actually interested in the underlying elementary particles that bang into each other, the quarks and the gluons. Well, we need to be able to control the rate for these completely ordinary processes to high accuracy in order to look for the comparatively rare processes that might be signals of new physics. So for instance, a process that happens hundreds of thousands of times a second that you have to learn to control is two gluons inside the protons that keep the quark inside the proton. Two gluons come in, they bang into each other, and three gluons go out, or four gluons go out. And we don't see them as individual gluons. They come out as jets of strongly interacting particles. But anyway, we'd like to know what this underlying process, what the amplitude is, what the rate is for it to happen in order to be able to subtract it and look for ordinary things. Naively, this is completely ordinary physics that we've understood for a long time. And how would we go about doing this calculation? Well, we open up the textbooks. Feynman taught us how to do these calculations over 60 years ago. We're in the leading order of approximation. Let's say I have two particles in and four out. I would just draw all these pictures. And these are all the different ways in which the gluons could have come in and banged into each other in various ways to go out. And okay, it just looks like it's a little complicated. There's many, many diagrams, tens of thousands of terms if you actually just sit down and do it. This is a picture of what you would get, something like 100 pages of dense looking algebra like this if you actually look at the sort of final answer. And okay, that's just what it looks like. And there's no a priori reason to expect the answer is simple. It looks like you're asking a complicated question and you get a complicated answer. Maybe you're not that surprised, but physics has a great way of rewarding morally good behavior. And the theorists who have to do these calculations because experimentalists needed to know the answer, a little over 30 years ago, they discovered something astonishing, that these hundreds of pages of algebra in many cases collapse to a single term. And so, if I talk about the amplitude for the collision of these gluons, depending on the spins or the helicities of the gluons, in some configurations, the answer is just a stunning one-line expression. I haven't explained to you what these brackets mean, but when you see a bracket 1, 2, roughly it's a square root of the dot product of the momenta of the corresponding particles. Okay, so this is another indication, nothing to do with this highfalutin philosophy, another indication that the standard way of organizing a way about this physics, Feynman's way of doing this physics, and remember, why is this way famous? It's because it allows us to make the usual rules of space-time and quantum mechanics manifest. So we make the rules of space-time and quantum mechanics manifest, perfectly correct, spectacularly successful, but it would make you think the answer is hundreds of pages of algebra. But it isn't. The answer is just this one term. So that is a strong sort of practical motivation that maybe these formulas, these amplitudes, these functions are also the answer to a different question. And maybe if we understand what different question actually gives us these incredibly simple answers, it'll expose other principles as primary. It clearly won't make space-time and quantum mechanics primary. If those are primary, there's nothing better you can do than Feynman and its hundreds of pages of algebra. But if we make some other principles manifest, perhaps we'll understand where these simple formulas come from, and maybe that's a clue to how we can actually get things that are compatible with the principles of space-time and quantum mechanics to begin with. Okay, so that's the kind of clue that we can follow up on. And I can't resist saying that it's not just that the answers are simple, the answers have incredible, amazing hidden symmetries. So for instance, if I think about the collisions of these gluons and I label the gluons P1, P2, the momenta P1, P2, P3 up to P6 in this example, we have momentum conservation that tells me that all these momenta add up to 0. So I can denote the momenta as sort of little vectors on a 4-dimensional piece of paper, and I would get a closed polygon. Well, the incredible thing that people experimentally noticed by staring at the results is that the answer is the same if you invert the coordinates in the picture in which this in the picture in which this polygon is drawn. That's a totally hidden symmetry. It's called a dual conformal symmetry, dual inversions or dual conformal symmetry. And in fact, that hidden symmetry together with the obvious symmetries turn into an infinite number of symmetries that the amplitude has. It's known as the Yangian symmetry, technically the Yangian symmetry of SL4/4. What's remarkable about this might sound like some very abstruse thing that only a few mathematical physicists might care about. But in fact, this isn't some abstruse symmetry. It contains and generalizes an ancient symmetry going all the way back to Newton. This the symmetry that the Kepler problem has associated with the Runge-Lenz vector that explains why planetary orbits are ellipses. So that ancient amazing fact about orbits being ellipses in the 21st century is related to this remarkable hidden Yangian symmetry of the gluon amplitudes. And I should say that this observation was one of a large N of brilliant and beautiful results of your own Simone Taron-Huot from a number of years ago. So that's why I couldn't resist mentioning it here. Okay, so now we've seen there are sort of two indications. First, there are all these highfalutin reasons that we should somehow find some way of thinking about physics that's the space-time quantum mechanics physics in a way that doesn't hardwire in those notions. And secondly, there's this practical indication. If you do hardwire in the notions the way we do in textbooks, we get horrendously complicated results, hiding all these infinite symmetries. So we should find some way of thinking about the physics that exposes those things instead. Okay? So those threads, the highfalutin thread and this more concrete thread are connected to each other. So we can ask the question again, is there a deeper structure underlying space-time and quantum mechanics? And if there is, I think it's pretty clear that it has to involve some deep new ideas. Clearly has to involve deep new physical ideas, and it's also pretty obvious ahead of time that it has to involve new mathematical ideas too. There's no way, if we're going to ditch the usual formalism, these amplitudes are very cool, complicated, intricate functions of the momenta of the incoming particles and their helicities, their spins and so on. If we're going to get that from a different starting point, it has to have some beef in order to be able to produce such remarkable objects. It can't be some Mickey Mouse thing. Okay, so, all right, so I want to give some ideas of what the physical and mathematical ideas are. So in order to talk about the physical idea, well, I mean, we don't know what they all are, and we don't even know if this general program is ultimately on the right track. But what we've been seeing so far is exposing a basic kind of physical idea and a basic kind of mathematical idea, and I want to tell you what those are. The basic physical idea is encapsulated in this dichotomy between on-shell versus off-shell. And so what is this dichotomy? Well, let's think about like a particle moving around. Okay, so if we just have a particle freely propagating around that has some momentum, some energy and some momentum that we group into a 4 momentum, and E squared minus P squared is equal to M squared. So that's what we mean by it being on shell. It has 4 components. E and P is 4 components, but they're constrained to be on the mass shell where E squared minus P squared is equal to 0. Okay, so those are physical particles. They're labeled by 3 things. 3 momenta, and that fixes the energy. But when we imagine these particles bang into each other and we draw these pictures that Feynman tells us about, let's say I look at this picture. In this intermediate line here, if the particles on the outside have momentum P1 and P2, then by momentum conservation, the guy in the middle has to have momentum P1 plus P2. But then in general, even if all of the external momenta are on shell, it's not going to be true that P1 plus P2 squared is equal to M squared. These intermediate guys are not on shell. We say they're off shell. Sometimes we say they're virtual particles. Okay, so this idea of virtual particles is absolutely ubiquitous in our thinking about quantum field theory in the usual way of doing things. And yet it's also funny that they're not, as their name suggests, they're not really there. No detector actually sees them. We only see these particles that propagate out to infinity. And in fact, this difference between real and virtual is really the heart of why these Feynman diagram calculations are so horrendously complicated. So the things that are real are the particles that propagate out to infinity and are seen in detectors. All the stuff in the middle, these virtual particles in the scattering process, those are the things that we make up as theorists, or Feynman made up as a theorist. They don't propagate over infinite distances. They only stay here in the middle. They're kind of a fiction incredibly useful fiction that we introduced to manifest the rules of space-time and quantum mechanics. And but it's also fascinating that exactly this fiction of virtual particles is directly the origin of all the horrible complexity we see in the answer that in the intermediate stages of the answer that sort of miraculously cancels out when we sum everything up. Okay, so there's a kind of a basic physical idea here. We want to eliminate the notion of virtual particles. Somehow think about the physics where we never talk about virtual particles. And if we're not going to talk about virtual particles, well, how could we possibly get a handle on the fact that we use this idea of a virtual particle in order to be able to describe this interaction that's taking place at a point in space-time? We can have locality. We have the principles of quantum mechanics. Those things are useful. So how are we going to get those? How are we going to get those properties if we're not talking about virtual particles? Well, it's useful to go back and actually see how we see the principles of locality and of unitarity actually reflected in the physical answer. Let's say I have, again, this simple process where 1, 2 bang into each other, go to 3, 4, and they're doing it sort of by the exchange of this intermediate guy here that has some mass m. Well, it's clear that if you tune the energies of the incoming particles such that you can actually produce as a physical state this intermediate guy of mass m, then like in every such thing that we're familiar with in both classical and quantum mechanics, we should have a resonance, right? When you're kicking something at exactly the right frequency, you should have a resonance. When you have a resonance, amplitudes blow up. And so we should expect to have a resonance or a blowing up of the amplitude for this process precisely when you tune the momenta of the external particles such that P1 plus P2 squared is equal to m squared. And so that means that the amplitude itself actually has a pole. It has a divergence, at least approximately, it has a divergence that looks like this 1 over P1 plus P2 squared minus m squared multiplied by something. Again, this pole is there when a virtual particle actually becomes real, when you tune the external momenta for that to happen. Now, so that's one thing. The amplitude should have poles when P1 plus P2 squared is equal to m squared. It shouldn't have random other poles. For example, it shouldn't have poles when P1 plus P2 squared times P2 plus P3 squared minus something to the fourth is equal to zero. That pole does not have any interpretation of the particles meeting, producing something, and having it go out. The only reason this thing should blow up is if you're on resonance. So the fact that the interactions are local in space-time is telling us that the amplitude can have poles, but only very particular kinds of poles that we can interpret as virtual particles becoming real. But quantum mechanics tells us more. In the neighborhood of this pole, what's actually happening? Well, we just said it. What's happening is that you're producing this particle, then it goes a long distance and it decays again. So that means that the amplitude, right sitting on this pole, the kind of residue on that pole should actually factorize. It should have the interpretation of having produced the intermediate particle and having the intermediate particle go back out and decay to 3 and 4. So we've learned something interesting here, that the rules of space-time and quantum mechanics are actually reflected in very simple mathematical properties of this amplitude, at least for these simple examples, for the kind of simplest processes that we're talking about. Locality tells us that the only kind of singularities this object can have are poles when a sum of the subset of the momenta can produce a real particle inside. So when a sum of the subset of the momenta goes on shell. And unitarity tells us that when that happens, the actual amplitude has to factorize. So if I have 3 in and 3 out, and I tune P1 plus P2 plus P3 squared to go to m squared, so I can make an intermediate state here, the amplitude should factorize. There's the 1 over P squared minus m squared there, and should factorize to the amplitude for 1, 2, 3, producing this intermediate guy on the left and something similar on the right. Okay, so and this now.
I don't want to interrupt, but you have 10 minutes according to the standard schedule. We
okay.
can go a little.
All right.
I know.
Great. Yeah. Oh, good. Yeah. Fine. Okay. So this defines a sort of a concrete program for us. Given that we see how the usual rules are of space-time and quantum mechanics are reflected in the answer, we can try to find a different question that gives these functions with no reference to space-time or quantum mechanics, but which nonetheless somehow gives the correct poles and the correct factorization. And in other words, we have to find some different rationale for functions that give us poles in the right spot and factorize in the right spot. Okay, so that's the physical idea, is to eliminate virtual particles and hunt around for some structure then that is going to produce the same functions from a different starting point. So now let me tell you what some of the mathematical ideas are that have been seen. So the mathematical ideas are associated with these notions of, in the title of my talk, of positive geometries living at infinity. So what is a positive geometry? Well, the simplest example of a positive geometry is like the inside of a triangle or a cube or a higher dimensional polyhedra, and they have generalizations to similar shapes, but which are curvy, which have sort of curvy boundaries. What's important about all these examples, it's some sort of compact region, and it has boundaries of all possible dimensions. So, if you have a cube, it's a 3-dimensional shape. It has faces that are 2-dimensional, edges that are 1-dimensional, and vertices that are 0-dimensional. Whereas if you have a sphere, it has an interior, it has a boundary that's 2-dimensional, but it doesn't have any boundaries after that. So a sphere would not be a positive geometry, but the interior of a cube would be. Okay, so there's this sort of general notion of positive geometry, that they're real geometry. And interestingly associated with these real geometries is a certain sort of analytic object. It's a certain form, function, or more technically a differential form. But this differential form is completely locked by the geometry. It's completely determined by the properties that this form should have poles. It should blow up only when you hit the boundaries of this geometry. and it should do so in a sort of consistent recursive way. So if it blows up once, if it has a single pole, if you take the residue on that pole, you're stuck to one of the facets of this geometry, and then you can keep going. So you can recursively take successively take more and more poles, so the only singularities you will ever see are on the boundaries of the geometry. So that's the basic idea. There's a geometric shape, and the geometric shape dictates a certain function. Now, these positive geometries are going to actually end up really living in the what we can call the kinematical space that labels the on-shell particles going to infinity. You know, if you have n particle scattering, we have n on-shell momenta going to infinity. Typically, we talk about massless particles. So we have sort of n massless momenta going to infinity. And basically, in that space of the n momenta, we identify some geometric region. That's this positive geometry. That geometric region determines this complex form, and we actually directly associate the scattering amplitude with the form. Okay, so this is a different kind of question. There's no interior of the space-time. We just have, but instead we find these geometries that live in kinematic space, and the amplitude is determined by the fact that it has singularities on the boundaries of this object. Now, one of the very interesting things, and now you can ask, well, how do we know what these geometries are? Well, it turns out that once you go to these kinematic spaces and you look at them a little bit, they're very simple and natural, but fundamentally combinatorial questions and ideas in this kinematic space that in turn determine the geometry. So it's like you go to this kinematic space of n null momenta, you find a little bit of extra structure and natural combinatorial question in that space that determines a geometry that in turn determines a form that you can associate with the scattering amplitude. I don't have time to go through these examples in any detail, but just so you see some sort of rough idea of what I'm talking about. If our positive geometry was just the inside of an interval, then the form that we talk about would just be the form that has poles at x equals a and x equals b. So it would be this form. If it was a triangle, it would be a form that has singularities on all the three boundaries of the triangle. But the second the shapes start getting more complicated, the forms have to start getting more interesting as well, because if you just write down the most obvious thing that you can, it would have singularities in all kinds of other places other than just the edges and vertices of the shapes that you're talking about. So that's where the sort of beef starts coming in, that these forms can start getting quite intricate and interesting, even for these very, very simple cases like squares and pentagons, never mind their higher dimensional generalizations. But one thing that you immediately see is that I told you that the amplitude is essentially determined by this form, now this form has singularities on the when you hit the boundaries of the geometry. So we learned that the singularities of the amplitude are associated with the boundaries of the faces of this geometry. So that now it starts giving a more geometric flavor to what it is that we're looking for. We want to understand somehow why are the poles in the right spot and why the amplitudes factorize on those poles, and that starts getting translated to a question. You have a certain kind of geometry, but it has to have some magical property that when you go to its boundary, you discover that on that face you get something that actually factorizes into the product of two smaller geometries of the same sort. Okay, so again, we're sort of getting things more concrete as we go here. Okay, so let me just, in the last few minutes, give you a first invitation to these ideas. The sort of rest of the colloquium is working through a sort of second example in more detail, where you can really see, starting from basic picture of combinatorics and going all the way to something that determines an amplitude. But given the time, maybe I'll just go through this first invitation just to give you a flavor of the sort of thing that we're talking about. So I just want you to get an idea of why funny, weird geometric things might be related to these questions at all, because this is not meant to be obvious. It's not sort of remotely obvious that such a connection exists. So I want to give you some idea for why such a connection should exist. Actually, ironically, what I'm just about to tell you about was understood relatively recently. The sort of first invitation was only understood maybe 2.5 years ago, after much more, in other ways, more sophisticated and more difficult things were understood. But anyway, I'm happy to be able to give a relatively simple example so you can get a flavor of what's going on. So let's imagine that we're talking about the sort of simplest theory we could imagine, just the theory of interacting spin zero particles. It could be like interactions of the Higgs particle. The second part of the colloquium is really about the gluons, what we really practically care about at the even at the LHC. But anyway, this is a perfectly good sort of toy set of examples to talk about. And so what we would do, we'd imagine we sort of label the particles 1, 2, 3, 4 up to n. And again, if I was just drawing things at leading order of interaction, I would draw these pictures. If there are 2 in and 2 out, I would draw these pictures. If there's a total of 6 particles scattering, just these simple tree diagrams. An important thing is that all these things are ordered on the outside. 1, 2, 3, 4, 5, 6. They're sort of ordered clockwise as we go on the outside. Now, something that you can see, the only momenta that you'll ever see in these pictures, for example, in this bottom picture, I can see this intermediate line has momentum P1 plus P2. That one has momentum P1 plus P2 plus P3, and so on. The only poles that we ever see are sums of consecutive momenta like this, squared minus m squared. And so we can go back to the picture I mentioned before, where we draw all the momenta end to end on a piece of paper. And if we do that, then we can see that we can actually interpret this sucker as just nicely as the distance squared between 2 points in this picture. Okay, so in other words, every one of these diagrams, every sort of intermediate line I see, I can associate with a chord in this polygon. Okay, and this polygon where the edges are the momenta of the particles. Now, a nice question to ask is: imagine that some lazy but smart experimentalists who skipped the class where they were taught how to do these calculations, they just were somehow handed the measurements of the answers, or they could have their fingers on the dial to move the momenta around however they wanted. You can ask, what would they notice about these functions? And clearly they would notice that these blow up somewhere. They would notice the resonance phenomenon. Okay, so they would notice that when you can tune the momentum for 1 and 2 and make the amplitude blow up. Once they did that, they'd be excited. They think, could you make it blow up more? So in other words, there's a single pole. Could they get 2 poles? Could they get 3 poles? And so on. And if they just had 2 in and 2 out, they would discover that it only blows up when P1 plus P2 squared goes to m squared, or when P2 plus P3 squared goes to m squared. That would correspond to this first picture, this guy becoming real, or that guy becoming real, but not both. Okay. If they went to the next example at 5 points, there would be a pattern in this blowing up again. They would notice that I could have P1 plus P2 squared go to m squared, and then also P1 plus P2 plus P3 squared goes to m squared, but I can't do these things in other combinations. If they looked at this in the picture of this polygon, they would see, for example, I could have a pole when this variable, this diagonal goes to 0, or that diagonal, when this diagonal goes on shell, or that diagonal goes on shell, but not both. At 5 points, they would notice this pair of poles are allowed to be seen together, but this pair are not. And it's interesting that the pairs that are not are the ones that are crossing. And in fact, this is a general feature here. This is a way that the principles are reflected in this example. It's just a special case of what I was saying a few moments ago. If you're just handed these, amplitudes, they depend on these variables that we can associate with chords of the polygon, and the principles of locality and of unitarity are reflected here. Locality is reflected by the fact that the poles can't occur together randomly. They only can occur together in a ways that these chords in the polygon don't cross. And once that's true, unitarity is reflected in the fact that when you put a particle on shell corresponding to one of these chords, the answer, the residue on that pole, actually has to factorize into the product of one polygon on the left here and the other polygon on the right, just as if you sort of cut the polygon along that line. Okay, so once again, now we have the sort of sharper version of the question: what kind of structure can we imagine that would sort of give us this ab initio from a different starting point? And an observation that this lazy but smart experimentalist could make is the following. Let's say they were trying to explain the pattern that they just saw. They would notice that for 4 and 5 points, that this pattern could actually be represented graphically. For instance, I'll do the 5-point example. They would notice that if they drew, if they said that you could have just you could have a single pole and then 2 poles together, a single blowing up and then 2 blowings up together. Then, for example, they could have a single pole that corresponds to this chord, but then the next pole that they could have, they could either add this guy that doesn't cross it, or this guy, or this guy that doesn't cross it. And then, sort of slightly remarkably, all the pattern of the poles can actually fit on this interesting picture of a pentagon. So in fact, now you can think of the vertices of the pentagon as corresponding to complete triangulations of this of the 5-point pentagon that we started with. The fact that the shapes are the same is a complete coincidence here. We'll see a slightly more interesting example in a second. But it's sort of non-trivial that the pattern of poles that are compatible with locality sort of fit and can be represented in this graphical way as a shape. In fact, it's much more interesting when we go to 6 points. So when we go to 6-point scattering, it's not obvious at all. And it was discovered, from an analogous question, it was discovered by mathematicians in the late 1960s that all of the pictures, all the possible pattern of poles actually fit into this beautiful 3-dimensional shape. And in general, for any number of particles, this is true. And these objects are known as the Stashev polytope after the discoverer Jim Stashev, or more generally as the icosahedron. So this is extremely interesting. It's not obvious from the definition in terms of particles moving in space-time that it should be possible to represent all the possible allowed pattern of how the poles come together in a shape, but it is. And even more interestingly, this shape also explains where factorization comes from. How does it do that? It does it in the following way. Remember, even roughly, we have the idea that we have these geometries, and the facets of the geometries, the boundaries, should correspond to poles of the amplitude somehow. So the way we see factorization is the following remarkable feature of the icosahedron, which is that if you take an icosahedron and you go to its boundary, the facets you see on the boundary are actually direct products of lower icosahedron. So we can see that here. This is the same picture again. You'll notice it has 5 faces that look like pentagons, and sorry, 6 faces that look like pentagons and 3 that look like squares. Well, all the facets that are pentagons, that pentagon, a pentagon is of course the same as a pentagon, a direct product of points. And I just told you that the shape of the pentagon corresponds to 5-particle scatter. So this facet, this pentagonal facet, is that factorization of the amplitude that has 5 points on the left and 3 points on the right, the way I have drawn here. On the other hand, we have these square faces. Now, a square is, of course, the direct product of an interval in one direction and an interval in the other direction. And I just told you that an interval is what we got for 4-point scattering. I don't think I said it explicitly, but in this example, even more simple than the 5-point one, the picture associated with the poles of the 4-point is just an interval. On one end, you have the one factorization channel. On the other end, you have the other one. Okay, so it's a fascinating fact that the pattern in which the amplitudes can blow up together can actually fit on a geometry. So this is the pattern that we would see in the kinematic data at infinity. In these x's, these chords of the polygon are just part of the data that labels the momenta that we measure, the onshore momenta that we actually measure at infinity. And the pattern of how the amplitude blows up as a function of those variables remarkably fits into this shape. Even though it's not manifest, it remarkably fits into the shape. And that shape actually also tells you that the amplitudes factorize because it has this remarkable property of factorizing on its boundary. Okay, so as I said, that's the invitation that's just meant to give you some taste that some kind of geometric ideas living in kinematic space are exposing some hidden things about the amplitudes. And I now don't have time to talk about the sort of, in a sense, second half of the colloquium, but I can say that there's a very similar, there's actually in some sense an even simpler but more subtle set of ideas that were sort of historically discovered first in this sort of somewhat more complicated setting, directly related to pictures for gluon scattering. And as you at least very impressionistically can see from the slides as I'm flipping through them, the ultimate underlying ideas have to do with the representations of permutations. So there's some extremely basic mathematics related to representations of permutations that after you start following it up, ends up being associated with some fascinating geometric structures. And these geometric structures are really generalizations of the notions of polygons and polyhedra into slightly more abstract mathematical settings. So these are now positive geometries that live in the kinematic space associated with the momenta of gluons going out to infinity. They're curvy, but once again, these interesting sort of combinatorial questions in that kinematic space determines these objects known as amplituhedra. As leading order of approximation, they give you the amplitudes even for gluons that we would scatter at the LHC. But if we include all the quantum corrections as well, it works for a special limit of maximally supersymmetric theories of gluons. And of course, where many people are trying to figure out how to extend these things to totally non-supersymmetric settings. This invitation I was telling you about has nothing to do with it's a very general thing about theories of scalars. And in fact, what I told you about the pattern of how the poles come together has even nothing to do with scalars. This is a totally universal thing about the way locality and unitarity, at least in leading approximation, are captured invariantly by some geometry. And it actually works also beyond leading order of approximation as well. And that's something that we're in the middle of trying to figure out in complete generality. So let me just end it there. And just say that over the past decade, we have been seeing some concrete examples where the rules of spacetime and quantum mechanics, locality and unitarity, emerge from simple new mathematical structures living in this kinematic space at infinity. There's the story I didn't tell you about of amplituhedra for gluons, theories of gluons and maximally supersymmetric theories in the planar limit, including all quantum corrections. There are these associahedra and their generalizations for completely non-supersymmetric scalar theories, and as I said, capturing rather universal features of amplitudes for all theories. These ideas have surprising relations to active branches of mathematics that have been independently developed in the past 15 years. So they're not ancient parts of math. Most of the words didn't even exist 15 years ago. But it's one of the sort of wonderful surprises. This is not the part of mathematics that has ever had anything to do with physics. They're very combinatorial ideas in algebras, total positivity, cluster algebras. Other parts of this subject involve notions from number theory. These are sort of things that have not typically had any interaction with physics before, and it's startling to see them have not only interaction with physics, but not esoteric physics, but bread and butter, physics of the real world that we see when we look out the window. And there's also, from at least some of these ideas, quite recently, some fascinating relations to string theory, even though there's no strings in sight here. Of course, good ideas are ideas that non-trivial ideas are all connected somehow, and there are some really fascinating relations to a string theory that are starting to be evoked. But really, to me, the most conceptually exciting thing is that we are seeing examples, and even though I didn't show you a very detailed examples, already this picture of the associahedron, I hope, gives you an idea of what we're talking about. You see, there's this autonomous mathematical object that exists in the Platonic world of ideas. It has some, you can actually discover it by asking very natural questions in the kinematic space of the momenta that we measure at infinity. And that autonomous object has these remarkable properties. It has facets of a very particular type that we can associate with the correct poles. And it has this amazing feature that when you go to a facet, what you see is the direct product of two lower things of the same type, which we can interpret as being the unitarity of quantum mechanical evolution. That's the sort of thing that we're seeing in and trying to understand more in examples, what these autonomous objects are, what kind of questions we have to ask in this kinematic space in order to reveal them, what kind of questions reveal these positive geometries, and how can we build more and more of a dictionary for connecting those sort of abstract combinatorial geometric ideas to the actual amplitudes that we see. We understand how things work in a number of examples, but we'd like to understand it in more and more examples, and of course get closer and closer to the real world. Okay, thank you very much.
Oh, thank you very much, Professor Arkani-Hamed. If you enjoyed the talk, and I'm sure many people did, please, if you can, use your clapping icon in Zoom or on YouTube, say something in the chat about how much you enjoyed it. So I'll address the questions now. In Zoom, if you would like to ask a question, please raise your hand icon. In YouTube, if you'd like to ask a question, please type it into the chat and it will be communicated to me. I'll go back and forth. I don't think we're going to have time for all the questions because we had a lot of questions and we're a little over time. But we'll try to get as many as we can. So I'll first ask, I'll go in order here. Jim Klein has asked a question. Jim, can you please unmute yourself and you can turn your video on.
Yeah, you briefly mentioned it, I think, but what's the status of trying to extend these to these ideas to non-supersymmetric models? Because I think that's one of the things that you rely upon for many of these results, if I'm not mistaken.
Well, and what I was in fact, what the only part I actually sort of concretely got to talk about was the totally non-supersymmetric things. Okay. So there's a structure for essentially, well, I mean, they're being understood at various levels. For phi cube theory, for planar phi cube theory, okay? So you can call it it's the bi-adjoint phi cube theory, but really it's an excuse to just draw, it has nothing to do with planarity even. It's an excuse to draw the same diagrams that we draw for gluons, except forgetting about the polarization. Okay, so we're just summing all those diagrams. At tree level and at one loop, just as of December, as a tree level, we've understood for a while. At one loop, it's understood what these geometries are, very much along the lines of what I was saying. And essentially, what I've been doing with my friends over the pandemic is figuring out how this works to all loop order. To all loop order, and has nothing to do with planarity. So really, it does have to do with the usual genus expansion, 1/n expansion. Okay, so we do organize thinking about our diagrams order by order in 1/n, but for any surface, there what we're, I mean, we understand that 2 loops, 3 loops, many on tori and so on. We're trying to understand it in complete generality, but there is supposed to be an idea that there is a geometric object associated with any Riemann surface on which we draw our Feynman diagrams. And that object is the positive geometry whose canonical form captures the corresponding integrand for the scattering amplitude. This is what connects it to these topics of cluster algebras and so on and so forth, because you would think there's not much new to say about the theory of two-dimensional surfaces, but that's one of the fascinating things of the last 15 years. There is this hidden, geometric algebraic structure associated even with Riemann surfaces. And that structure seems to be intimately related to these questions we can ask in kinematic space that bring to life these polytopes. So that's already something that's totally non-supersymmetric in any number of dimensions. Supersymmetry does not seem to be, to me, the critical part of the story. The more critical part is that everything that we've been doing so far is, and if I say, if we go back to the story of the amplituhedron and with gluons, if you take any theory in the Planar limit, but it doesn't have to be supersymmetric. Any theory has a certain universal kind of long distance singularities, factorization, soft limits, and so on. If you have a garden variety theory, not a gauge theory, totally garden variety theory, they all have factorization singularities. If you have a gauge theory, they also have soft singularities as well. And just like there's this, just like it's non-trivial that all the singularities associated with factorization are associated with the geometry. That's just what I showed you in this picture of the icosahedron. It's also non-trivial that all the singularities associated with both factorization and soft, everything, all the singularities associated with gluons are also captured by geometry, and that's the amplituhedron. Those things are just universal and true, it has nothing to do with supersymmetry. The extra fact that's interesting in supersymmetric theories and in this sort of phi to the p examples is that just giving that information about what the long distance factorizations looks like suffices to completely determine the object that you're interested in. More general theories also have life in the ultraviolet. They have, ultraviolet divergences, the renormalization group running, all of that stuff. So that's the real thing which is missing. I think that the real thing which is missing is to also figure out how to connect this sort of surprising geometrization of geometrization of all possible consistent singularities that are forced on us by locality and unitarity. How do we connect those to the singularities in the ultraviolet that we normally think of in the usual Wilsonian way? Okay, so that's, I think, the sort of one of the biggest challenges in this subject. But there are indications that something like that should be possible, because there are very, very similar mathematical structures show up when people think about the RG in not in the usual Wilsonian way that we think about as physicists, but in more graphical ways. Dirk Kreimer and Alan Kahn and friends, a little over 20 years ago, found this some interesting algebraic structures associated with the renormalization group, and there's at least some superficial similarities between those structures and the things that we've been seeing. So anyway, but what I want to stress is it's not that the supersymmetry is an absolutely critical thing. We even have these other examples that are totally non-supersymmetric. The thing which is important is that so far we're focusing on theories where the infrared totally determines what the physics is, and they don't have sort of life in the ultraviolet. There's no running, there's no UV divergences, there's no RG, interesting RG.
Thanks for clarifying that, Nima.
Okay, thank you. We have a lot of questions and maybe only 5 to 7 minutes for the rest of them. Jim, can you please unmute or mute yourself again? Thanks. So the next question comes from YouTube, and the question is it understood to some level or maybe completely how these polytopic ideas relate to intersection theory?
Oh yeah, I mean there are many. I think at zeroth order nothing is understood completely in this business. I mean, this is where and yeah. So there are of course there are obvious connections at various levels of depth between these things and intersection theory. Maybe sort of more specifically, intersection theory is a very general framework for thinking about the kind of singularities you get associated with integrals and so on. Anyway, it's a general framework for doing all kinds of things. Here, so far, we're sort of focused on a more special kind of singularity. We are focused on a situation where these geometric spaces completely determine interesting analytic objects just by the property of having these just logarithmic singularities, poles, simple poles at the level of rational functions. So it's not sampling sort of everything which is relevant in thinking about singularities of forms and integrals and so on. But it's clear that we have to go beyond that. This is related to Jim's question. If we want to also deal with the renormalization group from this sort of combinatorial geometric perspective, somehow we have to learn to deal with forms that are not just logarithmic, and to find some picture for how to make sense of that.
Okay, thanks. I'll go to another Zoom question. I think Robert Brandenberger had a question. So Robert, please go ahead and unmute yourself and turn on your video if you want.
Yeah. So Nima, my question was related to cosmology. So in cosmology, we don't have access to S matrix elements.
Sure, yeah.
We need to
Great.
compute intrinsic quantities.
Yes. Terrific question. Thank you. Yeah. So in fact, this was my original motivation for thinking about these things 10, 12 years ago was to think about the amplitude as a warm-up for cosmology. And in fact, so this kind of approach has started to be developed in cosmology. The whole, I would say that in the context of inflationary correlation. So if you think about let me back up a second. So you're absolutely right. When we have the S matrix, the observable is we do the incoming state, we look at what goes out, we can do the experiment over and over again, and that's how we get a precise quantum mechanical result. In cosmology, we don't have that. In cosmology, we don't have access to the initial state. All we can do is lie on our back and look at the sky and take advantage of the fact that the universe became huge, infinitely big in some approximation, if we ignore the fact that we're accelerating today. And so the experiment took place independently in different patches of the sky. So what we can do instead of doing the experiment over and over again is we can just measure spatial correlations, spatial averages, and those are the kind of observables that we talk about in cosmology. That's that's a pedantic way of talking about what we talk about. When we say, that we measure the density of hydrogen, that's a one-point function of the hydrogen number operator, right? So we just measure how much hydrogen there's in every box of a given volume, and we average across, moving the box across the whole sky. So, those are the things that the analog of the S matrix, we don't have access to the initial state. All we have are these cosmological correlators. That's it. However, it's extremely interesting that, so what is the data that labels some cosmological correlator? You have to give me a bunch of points in space, x1 through xn. We have translational invariance, so I can go to momentum space. So if the correlator is labeled by a bunch of momenta, k1 through kn, that satisfies momentum conservation because of translational invariance. You'll notice that the labels of a cosmological correlation function are almost exactly the same as the labels of a scattering amplitude. In all cases, we have a bunch of momenta that add up to 0. It's just that the scattering amplitude has one more condition. You interpret those momenta as the momenta of particles, so they have energy. So you also have energy conservation. In cosmology, we don't have energy conservation, but otherwise, the actual objects are almost exactly the same. They're both things that depend on n momenta that add up to 0. And just in the amplitudes, there's this extra condition that we have momentum conservation. So now, just like we've been exploring how we can think about the scattering amplitudes, even weakly coupled theories in perturbation theory along the lines of what I was just saying, we can explore how we can think about cosmological correlation functions in exactly the same way. And in fact, the similarity is very, very close in the context of inflation. So if we imagine inflation was generating these correlation functions, then once again, there's a picture of Feynman diagrams and all this kind of stuff that we do in cosmology to generate them. It's even more complicated than for amplitudes, as you know, much, much more complicated than for amplitudes to do the calculations using Feynman diagrams. And yet, just like with amplitudes, when people do the calculation, they get much, much simpler results than you would expect a priori. And so you can start doing exactly the same sort of on-shell philosophy in cosmology. What you want to do is find some way of directly determining the answer that only depends on a bunch of spatial momenta without ever seeing the variable t or eta. You never want to see an eta. You only want to see these k's and find some rules that determine the answer directly in terms of them. So that program, I think, is just getting off the ground. I would say it's sort of where amplitudes were 20 years ago. But people are starting to learn, how to just mechanically do the calculations without ever talking about the bulk. And of course, get to the answer much, much more quickly once you figure out what you're doing. This is, some people are calling this sort of cosmological bootstrap program. And you can look for some geometric structures analogous to these isosahedra and amplituhedra that might directly give you the answer. And even those, again, baby versions of them called cosmological polytopes have been found a couple of years ago. So I think there's a complete parallel for this program in cosmology that's just getting off the ground.
Okay, thank you. We're running out of time, but I
sorry. May I say one more thing quickly to Robert? I forgot to say this. Even somewhat more. This is a technically very simple point, but it's kind of mind-blowing anyway. If someone hands you these cosmological correlations, this is a static question only involving an average over space. But the remarkable thing is that if you knew the analytic form of these formulas, they have a certain analytic continuation, and they develop a certain kind of singularity when the sum of all the energies would be 0. Of course, by energies in cosmology, we just mean the magnitudes of these vectors. So we can't literally make them sum to 0, but by analytic continuation, you can. And remarkably, the residue on that singularity is the flat space scattering amplitude. So these cosmological correlations actually contain the S matrix in them. Not only is it not a different question, it's a slightly more general question that literally contains the S matrix inside it. So I find that absolutely mind-blowing, that the static question, you just sit on your back and look at the sky and measure these correlations, it contains in it the answer to totally dynamical questions about particles coming in and going out and banging into each other, once you can analytically continue away from the physical region. So there's a very deep connection between the cosmological question and the scattering amplitude one. And so the sort of instinct from 12 years ago that the amplitude was a warm-up for cosmology turned out to be much more true than I even hoped, because it's literally true that the amplitude lives in a kind of codimension 1 subspace of the story of the full cosmological correlation.
Thanks a lot.
Okay, thank you. Yeah, we have very little time left. We're over by about 15 minutes, but there is one burning question that came in from YouTube, and it is, what's Nima's favorite classical music?
Oh, come on, that's easy. Beethoven and Rachmaninoff.
Okay, with that,
whose isn't? Whose isn't?
Whose question? I'm not even sure. I mean,
No. This is like who would disagree? Yeah.
Oh, who could disagree? No, that's a good question. So with that, let's thank Professor Arkani-Hamed once more for a very nice talk. Please clap in Zoom or send something in the chat on YouTube.
Thanks very much, guys.
There are so many questions that we couldn't get to, and I'm sorry that we didn't have time for all of them. And with that, so I'll just thank everyone for tuning in on YouTube and for joining us in Zoom. Please come back next time for a talk by Marissa Justina from Google Research. She's going to talk about building Google's quantum computer. And with that, thank you very much.